So today we're going to be talking about van der Waals equation of state, especially at the critical point. We're going to derive some coefficient values for A and B. We're going to determine the compressibility factor for van der Waals equation of state at the critical point, and we're going to create a pressure volume diagram for water over a certain temperature range. Without further ado, let's go ahead and get into this. So before we jump into derivations and trying to find these values, we want to first look at, what does this equation of state especially mean? So let me drag this page over here. This is just a Wikipedia page about van der Waals equation of state that we're looking at here. And as we can see, we have this graph. And with this graph, we see where there is a marked critical point at this area right here. Now we know by calculus that at points of inflection, the second derivative is equal to 0. And if we look at this graph, we also see that that first derivative is also going to equal 0 because this is a straight horizontal tangent right here. So with that information, we can do a couple cool little things to go ahead and find out that final equation of state and find these coefficients here. So with all that being said, let's go ahead and get into this. So we're evaluating van der Waals equation of state at the critical point, and the critical point means we're going to have a critical temperature and a critical volume. Remember, there's only one combination of pressure, volume, and temperature that give us the critical point. We know that from this graph here, right? Critical point is going to be right there. So, having known all that, we know that temperature is going to be a constant, volume is going to be a constant, and we just want to take the derivatives of these, set them equal to 0, and then we're going to set them equal to each other to find these A and B values. So first, let's find the first derivative of volume with respect to, pressure with respect to volume at the critical point. So R, Tc, those are constants. Vc, that's a constant, minus B, that's a constant coefficient. So we're just going to go ahead, since this is to the -1 power, we're just going to do a power rule here. So since this is to -1, it's going to be a negative RTC over VC, V, not C, over critical volume minus B squared, right? For the second part, it's going to be the same thing. VC is a constant, A is a constant. So we're going to do a power rule here. VC is to the -2 power. And if we do a power rule, a negative times a negative, going to be a positive. And it's going to be 2A over VC cubed. And remember, this is going to be equal to 0. Let me just make this. There we are. That's going to be equal to 0 there. So we found that first derivative. Let's go find the second one then. So now d2p over dv squared at the critical point is going to be equal to, now we have the same thing basically. Now what's going to happen is you're going to have a negative times a negative is going to be a positive. So now it's going to be 2RTC over VC minus B cubed. And again, same thing for that. Now we're just going to have, we're just going to have a negative now. And it's going to be 3 times 2 is 6A over VC to the 4th. And remember, second derivative also going to be equal to 0. We have an inflection point there. So now we have these two equations here. All we have to do is set them equal to each other and solve for our coefficients. So now that we've gone ahead and derived our first and second derivatives, let's go ahead and try and solve our coefficients. So first thing we want to do, I'm just going to rewrite these equations so that there is one part on both sides. This side is equal to 0, so we can bring the left side over. And so we are left with RTC over VC minus B squared is equal to 2A over VC cubed. And let me just shove this over a little bit. My board lagged out. We're just gonna ignore that. VC minus B over VC minus B squared over, or sorry, equal to 2a over vc cubed. And the other equation is going to be 2rtc over vc minus b cubed equal to 6a over vc to the 4th. So now that we have these two equations, what we can end up doing is get a consolidated equation that includes both of these components by multiplying one equation by the reciprocal of the other. So what we're going to do is we're going to have, I'm going to do this one since this is higher in power than the other one, and we're just going to be essentially canceling things out. It'll make it a bit easier to look at. So we're going to have 2rtc over vc minus b cubed equal to 6a over vc to the 4th. And we are going to multiply this side by this over here. So we're going to multiply by the reciprocal. So vc minus b squared over RTC. And we're going to do the same for the other side. So multiply this one by the reciprocal of the other function right there. It's going to be VC cubed over 2a. And now essentially what we're going to do, we're just going to go through and cancel everything out. So let's get, this is going to go away. This is going to be to the first power. This is going to cancel out with this. And we're just going to be left with 2. This is going to cancel out with the bottom. It's just going to be 4 on top. This is going to cancel out with this, and that's just going to be 1. So now when we rewrite this equation, we are going to have 2 over VC minus B is equal to 4 over VC. So now what we want to do here is we're just going to collect like terms and simplify it that way. So first thing first, let's do it that way. So let's go ahead and we're just going to bring VC minus B over to the other side. So I'm just going to multiply on both sides by VC minus B. And we're going to divide both sides by 4. So over 4 over 4. So now what we're left with is this is going to cancel out with that. This cancels out here. Multiply by 4. We're just going to get 1/2 here. And that's going to be equal to, we have VC minus B over VC. 4's cancel out. So it's going to equal VC minus B over VC. And that can be further simplified into 1/2 equals 1 minus B over VC. So now let's go ahead and subtract 1 on either side. We have negative 1/2 is going to equal negative B over VC. And 1/2 is going to equal B over VC. And so eventually we just get VC over 2 equals B. So that's our first coefficient all done and derived. Actually, made a bit of a mistake here. I wrote that down as 4. That's actually supposed to be 3. So we're going to go ahead and just change all of those. So this one should be 3. This one, so we're going to divide both sides by 3. Let's see, so it's going to be 2 over 3, so that's going to change. 2 over 3. Oh boy. Math can be hard sometimes. Let's see. So this is going to be 2 over 3, so that's going to be minus 1/3. So 1/3 here. So B is actually equal to the critical volume divided by 3, and that's how that is derived. So now that we have b, solving a becomes very easy. We could just choose one of these or go back to our original simplified equation before we go through and cancel all that, and we could just plug it back in, try and get that a value out. So let's go ahead and do that next. Okay, so I'm going to go ahead and choose this top one here. It looks easier to deal with in my opinion. So let's go ahead and try and get our a value. So now we know that b is equal to vc over 3. So instead of having v there, we just plug in our new value, minus vc over 3 squared. Or actually, let's we have to set them equal to each other anyway, so let's go ahead and just do that from the get-go. Equals 2a over vc cubed. Okay. And so let's go ahead and try simplifying this out a little bit. So RTC is going to equal, so 1 minus 1/3, that's going to be 1 minus 1/3, it's going to be 2/3 squared equals 2a over vc cubed. That's going to square, so let's vc. So let's go ahead square both of those. So it's going to be RTC over 4/9 VC squared equals 2A over VC cubed, otherwise known as 9/4 times RT over VC squared equals 2A over VC cubed. Now we can go through, we can cancel out our VC terms. Let me get my red pen for that. That's going to be 1. So now we have 9/4 RT equals 2A over VC. And now we can multiply both sides by VC. 9/4 RT times VC. Well, remember, that's also critical temperature. Sorry, forgot to follow that through. Equals 2A. And now we can multiply both sides by 1/2. So now this becomes 9/8 R critical temperature times critical volume equals A. And that ends off with us deriving both A and B for the van der Waals equation. So now that we've found the A and B coefficients, we can go ahead and now find the compressibility factor. So the compressibility factor is this Z over here, which is equal to PV over RT. So we know the volume, it's the critical volume. We know the temperature, it's the critical temperature. We know R is the universal gas constant. However, we don't know our pressure yet. But since we have derived A and B, we can go ahead and find the critical pressure at the critical point. So let's go ahead and plug these in. Remember that, let's go RTC. Remember that VC minus B is equal to VC over 3 minus A is equal to 9/8 R times TC VC is equal to VC squared. So let's go ahead and simplify this a little bit. VC is going to cancel out. The numerator is going to have 1. That is going to be equal to, let me just scoot down a little bit here. This is going to be equal to RTC over 2/3 VC minus 9/8 RTC over VC. So further simplifying that down, we have, since we have a common coefficient for both of these, RTC over VC, let's just go ahead and shove that off to the side. So we're just left with subtracting our coefficients. This is 1 over 2/3, which is 3/2 minus 9/8 times RTC over VC. And so the common denominator, we just multiplied this by 4, so 12/8 minus 9/8 times RTC over VC. And that's going to be 3/8 3RTC over 8VC. And that is our critical pressure. So now that we have that, we can go ahead and substitute that into our compressibility factor. So let me just denote that. So now Z is going to be equal to 3/8 times RTC over VC times VC over RTC. Well, that happens to be quite convenient for us. These two cancel out, top, bottom here cancel out. All we are left with is 3/8. So our compressibility factor for the critical point is equal to 3/8. So now for this next part, what we're going to do is we are going to create a series of pressure volume diagrams for a certain temperature range. In this case, is going to be 275 Kelvin to 900 Kelvin. And we are going to create multiple pressure volume diagrams in increments of 25 degrees Kelvin using van der Waals equation of state. So let's just get the basics out of the way. We're going to import the NumPy library as NP, and we are going to, from, I believe it is SciPy, we're going to import make subplots. And from here, our coding may begin. So now what we want to do is, since everything is going to be in terms of the gas law constant, our critical temperature, and our critical pressure, we are just going to go ahead and enter these values. So remember, our universal gas law constant is 8.314, and we can look up TC and PV. So the critical temperature for water, we are dealing with water in this case. Let's just look it up, shall we? Let's see, critical temperature of water. Take a second to load because my computer's doing a million things at once. And we want that in Kelvin. So let's try and get that. Come on. Okay, we have 647.096 Kelvin. Just gonna Control C, Control V, easy enough. And that's gonna be in Kelvin, that's gonna be in joules per mole Kelvin. And our critical pressure, let's also look that up. Critical pressure of water. And we are looking for pascals. 22.064 megapascals. Okay, so to convert megapascals into pascals, we're just gonna multiply it by 10 to the 6. So 22.064 E6. That should give us our term in megapascals. Right? So now let's look up one more thing. And that's going to be A in terms of the gas law constant, critical temperature, critical pressure, same for B. So I have a Wikipedia page pulled up. And as we can see, our A and B values, too far. Our A and B values should be somewhere right around there. So we have A is equal to 2764, it's R squared TC squared over PC, and B is equal to 1/8 RTC over PC. So let's go ahead and get that in our, we'll get that in our code here. So A is going to equal 27 over 64 times r squared. Can I remember if it uses the double asterisk or the caret? I think it's double asterisk. R squared times TC squared all over was it P? Yeah, TC. I think that's right. Yep. So if we were to get our A constant, we get 0.553, some odd numbers. And so let's do the same thing for B now. It's going to be 1/8 times R times TC over BC. And so now we have our A and B coefficients for our van der Waals equation of state. So right now, you might be looking at your screen and telling me, hey, what's on there? What is that? Well, it sort of looks like van der Waals equation of state, except there's a very key difference. And that is this part right here. And so what we call this is the generic cubic equation of state. Generic cubic equation of state. The generic cubic equation of state. And in fact, instead of using the van der Waals equation of state, we're going to go ahead and use this generic cubic equation of state, right? So a couple things to note now. We have A as a function of temperature, which means that we're going to have to create a function that it takes inputs of temperature and gives us outputs of A, and then use those for our pressure volume diagrams. The other thing is now we have two new friends in play, and those friends' names are epsilon and sigma. Now, for this case, epsilon and sigma are just going to be equal to 0. So there's not too much to worry about here. It's just going to be this volume squared, which is the, with van der Waals, that's the assumption we make, that epsilon and sigma are, they're 0, and that A isn't this time-dependent thing, rather. So that's where we get that v squared from, if you see that. So let's go back into the Python code. Let's go ahead and try and create this function, shall we? So let's go ahead, let's try and create this function out, shall we? So we're going to define van der Waals pressure, and we're going to take inputs of V and T. Not the critical volume and not the critical temperature, but rather just V and T. These are volume and temperatures that we're going to be inputting into this equation, right? And so it helps to know what we want back from this, right? So we're going to go return, and we're just going to return van der Waals equation of state, that generic cubic equation of state that we saw, except epsilon and sigma are going to be 0, and so we just get that equation of state. So we give P is equal to, let me look back at the whiteboard. Oh, another thing I should bring up. For van der Waals equation of state, this A of T, which means there's a reduced temperature, it's not really that significant for this calculation, so I'm not going to go in and calculate a new A for each and every run of the graph. So we're just going to keep one A that's from the critical temperature, and we're just going to go and flow with that. So P is equal to RT over V minus B. So R times T over V minus B, right? And it's going to be minus, sorry, lowercase b here. And that is minus A over, well, A over V minus epsilon B times V minus sigma B. That looks right. So let's go in and define epsilon and sigma. Epsilon is going to be equal to 0. Sigma is going to be equal to 0. Remember, working with van der Waals here. And so if we hit that, why are you still giving me this? Epsilon and that should be defined now. And so let's run an input here. Let's see what it gives us, right? So what if we say van der Waals, what volume do we want? Let's just try some test volume. We're just going to go 1 to the -4th, or 1 to the 4th. And temperature, let's just go 300. Oh, sorry, VDWP. Multiply those, sorry. All right. So now that we have this function already and done, let's go ahead and create some volume and temperature values, shall we? So for this volume, we're gonna go ahead and we're gonna make this a np.log space. And we're using log because the idea behind the difference of magnitude between the density of a gas versus the density of a liquid, this thing could be orders and orders and orders of magnitude. So if we did a linear space, we probably wouldn't be able to see anything, and it would kind of just be a whole mumbo jumbo of things. It just wouldn't make sense to graph it in a linear space. So let's go ahead and we're going to use a logarithmic space for our volume. Now, the other thing we want to look at here is this V minus B. Now, B is representative of the amount of volume taken up by atoms. So we don't necessarily want this B to be equal to the V or the V to be equal to the B, because then it's a divide by zero error and it just doesn't make sense. So what we're going to end up doing is we're going to have our we're going to have that start value be log base 10 of 1.01 times B, so that we're not starting at a value that is equal to the volume, or we're not starting at a volume that is equal to B. Is it NP dot? Yeah. Okay, cool. Now let's see, what do we want to increment? Let's say we increment by 0.1 cubic meters, right? And let's end at, say, like 1,000. Right? So now if we look at our array V, have all of these volumes now, right? So it looks like we're ready to now just go ahead, plug these into a function and start graphing out our lines, right? See, we end at 10 to the -1. Yeah, that should be fine, I guess. So let's go ahead and try plotting all these out now. So now that we've gone and created our volumes, let's go ahead and start doing some graphing, right? So let's go, we're gonna create our subplot first off. So we're gonna go fig1 equals make subplots. And we don't necessarily have t values yet. However, we can just use a for loop to create our t values for us. So we're gonna go for t in, and we're gonna use something called np.arange. And it's going to take a starting value, 275 Kelvin, that's our starting value. 900 Kelvin is our ending value. And we're gonna go in increments of 25. Now, here's the thing about, here's the thing about that arange. As soon as it hits 900, it's not going to graph anymore, which means that it won't graph that 900 Kelvin line. So instead, we're gonna go 901 just to make sure that it can plot that 900 Kelvin. So now we're gonna go fig1 dot update scatter, or sorry, add scatter, and we know our x is gonna be equal to our volume, our y is equal to that van der Waals pressure, VDWP with inputs of volume and temp. And let's go mode is equal to lines. And we're gonna do something here to create our legend on the side. And what that is we're gonna go name equals F, which stands for format. We're gonna make this make these quotation marks, and we're gonna put T in these curly brackets, and then those are in units of K. And let's just plot this out. Let's see how it looks. Fig 1. Okay, so this thing looks huge, and there's not really a lot you can discern just looking at that. You can kind of see there's a bit of movement around there in that bottom little corner area, but we really want to edit this to make sure that it looks nicer. So let's go ahead and try and massage this out a bit, try and reformat it, make it look real nice. So now that we have a plot now, we see it goes to 900 Kelvin. Guess you really can't see that, but it does go to 900 Kelvin. If I scroll up, you can see that. All that's left to do really now is just reformat it, make it look nice and pretty. So let's go ahead and we're gonna go fig1.update scatter. Update. Spelling is hard. Update scatter. And we're gonna go, or actually, update x-axis. X-axis. We're gonna go ahead and turn this into a logarithmic. So type is gonna equal log. And let's just take a look at that. Let's see how that looks. It's taking a bit. Okay, we're starting to see a bit more separation between our lines now, so it's a good start. So let's also update our y-axis. Let's make it a range now, because I don't think we want to see up until 25 billion. That just seems absurd, no matter how way you cut it. So update y-axis, and we're gonna go. Let's go range is equal to. We'll go like 10 to the 8th. Let's go negative 1e8 to 1e8. Let's take a look. Let's see how that looks. Okay. Now we're starting to see a lot more difference here. I'm going to make it... how do I want to do that? I'll make it go up a bit more. Too much. Let's see how this turns out. 1e to the 9, that should take us to about 1 billion. You know what, I think we were good where we were at. We'll keep it that way. And so the last thing we want to do, let's just go fig1 dot update scatter. We'll go width is equal to 800 pixels, height, let's go like 600 pixels. What's the, how do you do that? Update layout, update layout. Okay, so now we see we have all of our different little lines here from 275 Kelvin to 900 Kelvin. We can see that even then, I don't want to go all the way out to 0.1. Let's go out to like 0.01, right? So let's go to the -2nd. I just really want to zoom in on the really pretty parts and not really where it flattens out. That's not as interesting. Sorry. Shift enter. Now we should be okay. Yeah, so we can really start seeing now If we look at this line, it's at 650 Kelvin, and 650 Kelvin, if you remember, is very close to our critical temperature, which is 647 Kelvin. So using these lines, we can see, if I isolate this one, you have this flattening out bit, that's going to be your critical temperature. Show all our plots. So that is how you would create a plot for using van der Waals equation of state for multiple temperatures.